This is Dr. T. Govardhan, Professor in Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, we are discussing the topic shear force and bend moment diagrams for cantilever beam subjected to point loads and uniformly distributed load. Here the cantilever beam. The cantilever beam is the beam in which one end is the fixed, other end is the free as shown in figure. Here the beam is always in a horizontal position. For this beam, we have to draw the shear force as well as the bend moment diagram when it is subjected to a point load at free ends as shown in figure. Let us consider L be the length of the beam, which considers the between the points A and B as shown in figure, and carries a point load W at free end B as shown in figure. Here at B, we are drawing shear force as well as the bend moment diagrams by considering left hand side point of the beam as our reference point. Now, with respect to the X, here now, the unbalanced force which is acting toward the right side is only B there now. That is at B, the point load is acting W in downward directions. So, with respect to the X now, that is X position, that is X section of the beam, the unbalanced force at B is given by W, that is which is acting downward directions. The effect of this force is always tends to slide the right side of the position of the beam in downward direction with respect to the left side. Hence, this force is treated as a positive shear force. So, the positive shear force always it is represented above the baseline. That means, while representing shear force diagram, first of all, draw the vertical lines passing through the various points or the key points of the beam in downward directions. Here, the distance between these two parallel lines is equal to the length of the beam now. At point B, here AB is representing the length of the beam. At B portions, the unbalanced force is equal to W, that is acting in downward directions. Hence, it is the positive. Hence, it is represented vertically upward directions. So, according to the certain units now. That is generally here taken as 1 centimeter is equal to 1 Newton force now. Like that, according to the scale, it is represented vertically upward directions. When you are moving toward the left hand side portions, that is up to X, the unbalanced force toward the right side remains constant only. That is the W. Again, when you are moving from X to again at A position now, that A point, the unbalanced force toward the right side remains constant, that is the W is acting vertical downward directions. Hence, the line is continuously, it is a parallel, that is remains constant up to A position now. Or in other words, it is in the form of rectangle. The length is representing the length of the beam, that is breadth is representing the shear force acting on the beam. It remains constant entire its length now. So here now we are representing generally Fx is equal to the unbalanced force is equal to W we are taking now. That is X is equal to 0, it remains constant. When X is equal to X remains constant, at A also it remains constant, hence it is represented as a rectangle now. Similarly, the bending moment at B, already discussed the bending moment at free end is always 0 for the cantilever now. That means at B is equal to 0. When you are moving at a point X now, the bending moment is equal to X is equal to W into X now. that is W into X. Since the effect of the force is tends to slide the beam in downward directions. That is, it is having just a hacking effect. That is inverted U shape. So, this type of bending moment is treated as a negative bending moment. Hence, it is represented the bending moment at x is equal to mx, which is equal to minus half w into x now. When x is equal to 0, the bending moment is equal to 0 now. Since there is no forces are acting between B to A now, hence the bending moment at A is represented as m into x, but x is equal to L now, hence it is represented as minus of W into L now. That is, the bending moment is gradually increasing in the form of straight lines, inclined straight lines from B to A as shown in figure now. That is, at B it is equal to 0, at x it is equal to W into x, at A point it is equal to W into L. If you draw just down the points, always it is in the form of straight line only. This is known as bending moment. The diagram is called bending moment diagram. These two diagrams are representing the magnitude of shear force as well as the bending moment at any given section can be easily determined by the numerical values. Here example problem number 1 now. Draw the shear force and bending moment diagram for the cantilever beam of span 1.5 meters carrying point load W1 equal to 1.5 kilonewtons as shown in figure 3 here now. The given. So here now the figure is cantilever beam is there now. The length of the beam is equal to 1.5 meters. It is equal to 1.5 meter between A and B. It carries W1 1.5 kilonewtons at it free end now. Now first draw the line which is passing through point to B as well as the A point like this. At your convenient distance, draw line to represent the length of the beam now. Here the force is acting in downward directions with respect to the point to X now, acting downward directions. Hence, that force is treated as a positive shear force. So here now the load is equal to 1.5 kilonewtons acting vertically downward directions. This 1.5 kilonewtons is also positive. It can be represented in a drawing as 1.5 centimeters. That means we are representing 1 centimeter length of the drawing is representing 1 kilonewtons now. That is 15 mm taking is vertically upward directions to represent the point load at W now. Since the unbalanced force remains constant from B to X now, hence the load is also, that is shear force also remains constant. Hence it is represented as horizontal lines from B to X position. Again, when you are considering shear force at a point here now, the unbalanced force at A is algebraic sum of the vertical forces which are acting on the beam, but only one force is acting in downward directions. Hence, the load is remains constant up to A also. Hence, draw the line, that is horizontal lines, to meet the vertical line which is passing from point A now. So, this diagram is representing the shear force diagram for the cantilever beam now. So, here now, that is shear force at B is equal to 1.5 kilonewtons. The shear force again, it is a positive because acting downward directions. At X is equal to again 1.5 kilonewtons. If A is equal to 1.5 kilometers, so that's we are taken, it is in the form of rectangle as shown in figure now. The bending moment diagram. The bending moment diagram is shown in figure now. See now. Again, draw the horizontal lines. to represent the length of the beam by drawing only vertical lines from the various sections of the beam. Now the effect of the bending moment effect of this pointed is it will deflect the beam in the form of inverted V shape, that is called hanging effect. Hence it is treated as a negative bending moment. So the bending moment at B is equal to, that is a force into distance. Since it is acting at a point, same point, it is treated as a zero now. Or in other words, the bending moment at the free end of the cantilever beam is treated as zero. Hence at B is equal to zero now. Now the bending moment at x is equal to, here at this point, it is equal to W into x now. W is equal to how much? 1.5 into x now. Since x value is changing now, hence the bending moment is also increases in the form of inclined straight line law now. Similarly, at a point here now, the bending moment is equal to W into x, W is equal to 1.5 kilonewtons. The length of the beam is also equal to 1.5. Hence, the bending moment at A is equal to 1.5 into 1.5, that is equal to 2.25 kilonewtons to meters. But the effect is having hanging effect, hence it is negative. Hence, negative represent to 2.25 according to the scale now. Join these 2 points. This is known as bending moment diagram. Similarly, this we are taking one more problem. Draw the shear force and bending moment diagram for cantilever beam of span 1.5 meters carrying a point towards as shown in figure 3A. This is a figure is known as 3A. The various forces which are acting on the points are shown in figure now. The given data is the length of the span is equal to 1.5 meters. The point related to B, that is the end is given 1.5 kilonewtons, and at point C it is equal to 2 kilonewtons is given now. The distance between B and C is given 0.5 meters now. Okay, we have to draw the shear force or the bending moment diagram for this beam now. So the shear force now. So first of all, draw the vertical lines passing through the key position of the beam now. That is the one at here B, where 1.5 kilonewton force is acting. The second one is at C, draw the vertical lines downward directions, where 2 kilonewton force is acting, and one more is the fixed end A position and so on. At a convenient distance, draw the horizontal lines to represent the length of the beam or axis of the beam. Now the given data, the problem is, first of all we have to draw the shear force diagram for this beam. The shear force at B is equal to, here B is equal to 1.5 kilonewton force is acting downward directions, else this value is treated as a positive force now. That is F from B is equal to where W1 is acting, which is equal to 1.5 kilonewtons. It is a positive force now. When we are moving along the beam from B to C position now, just before reaching the point C now, the shear force remains constant, and hence the shear force just up to the point C, it is equal to 1.5 kilonewtons only now. But at C, because of 2 kilonewtons is acting, suddenly the shear stress changes its values vertically to 1.5 to here additionally 2.2 kilonewtons. That is total force is equal to 1.5 plus 2 equal to 3.5 kilonewtons. That is draw the horizontal lines up to the point C to represent the unbalanced force of 1.5 kilonewtons. But at C is equal to 1.5 plus 2, it is equal to 3.5 kilonewtons. But this force is also acting downward directions, hence the shear force is equal to the 1.5 plus 2 equal to 3.5 kilonewtons, but acting downward directions, hence it is treated as a positive now. The bending moment here, the shear force at A is equal to, again now, one more point is there. Here there is no force acting between C and A now, hence the shear force at A is equal to the sum of the unbalanced forces which are acting toward the right side, that is 1.5 plus 2, both are acting downward directions, hence positive. That means at A is also equal to 3.5 kilonewtons. So by selecting suitable scale now, here we are taking 1 kilonewton is equal to 1 centimeters. So draw here now 15 mm upward direction to represent the shear force at a point B. Up to C there is no shear force now. Already we discussed. The horizontal lines, it suddenly increases to 3.5, that is 3.5 centimeters. After that it remains constant up to C. Hence this diagram is representing the shear force diagram. Generally it is now hatched here now internally to represent the diagram like this. This diagram is known as the shear force diagrams. Now bending moment diagrams. So the bending moment is always 0 at B now. Here now, even the force is acting, but it is a free hand. Generally taken as 0 only. So at B is equal to 0. That is bending moment at B is equal to 0. Similarly, the bending moment at C is equal to, it is a product of force and distance, may be taken that forces toward the right side or left side, but here we are considering all the forces toward the right side only. Hence 1.5 into 0.5 we have to take it now. So it is equal to 0.75 kilonewton meter, but the effect of the force is it slides the beam in the form of inverted U shape, that is called convexity. The effect is called hiking effect. Hence it is negative now. Negative means always represented downward directions like this. That is according to the scale 0.75 mm means assume just 1 kilonewton meter is equal to 1 centimeters. Hence 7.5 mm take downward directions. Since this is nothing but changing because of its length only, hence you have to join these 2 points by using straight lines now. Similarly, at A, we have to consider the bending moment created by the 1.5 kilonewtons as well as the 2 kilonewtons now. But both are tending to rotate when the beam in the form of inverted U shape, that is convexity at the top. Hence these two forces, these two bending moments are treated as negative only. Hence total bending moment at A is given by the sum of the bending moments created by the forces at B as well as the C, that is equal to 1.5 into 1.5, because the total length here B 1.5, total length is equal to 1.5 plus here 2 kilonewtons, the distance between A and C is equal to 1 and so on, which is total is equal to minus 4.25 kilonewton meter. Hence draw the lines vertically 4.25 from A and join with the here at C. Then this diagram is known as the bending moment diagram. When the cantilever is subjected to two loads at B and C as shown in figure now. After drawing, generally it is actually inside. This diagram is called bending moment diagram. So another problem it is there now. Here three forces are acting on the beam. Draw the shear force and bending moment diagram for the cantilever beam as shown in figure. Here the given data is the length of the beam is equal to 0.5 plus 0.7 plus 0.8, that is a total 2 meters is given. Similarly, at D, 800 newtons is acting downward directions, 500 newtons at C, and at B, 300 newtons as shown in figure. Now, in order to draw the shear force diagram now, First of all, draw the beam and represent the various forces which are acting on it as per the suitable scale. After that, draw the vertical lines in the downward directions from the A position like this. That is from D, C, B and A point to as shown in figure. Now, the shear force at D is equal to, at this point now, it is equal to 800 newtons. Since it is acting downward directions with respect to the point A, it is treated as a positive now. Similarly, the bending moment, the shear force, at C is equal to, up to just C, it is a horizontal now. There is no changes now. But at C, it is equal to 800 plus 500, which is equal to 1300 newtons. Again, it is the positive now. The shear force at B is equal to the sum of the forces 800 plus 500 plus 300. It is equal to 1600 newtons. The shear force at A is equal to, again, the sum of these three forces, or the shear force remains constant from B to A because there is no forces acting on it now. The 1600. First of all, take suitable scale now. That is, here we are taking 100 newtons is equal to, we are taking 1 mm now. 1 mm length of the drawing is equal to 100 mm. So, just 8 mm we are taking here from D, draw vertical line upward directions to represent the load of 1800 now. Since just before reaching the point C, there is no load is acting now, hence up to C position, it remains constant, or you have to draw the horizontal line now. But at C point, suddenly 500 load is that is acting now. The total load acting at C is equal to, it become cumulative, that is the sum of 800 plus 500, that is 1300, hence it is nothing but upward directions. And again, up to B point, it remains constant now, draw the horizontal line now. At B position now, again suddenly 300 downward force is acting, the sum becomes here 800 plus 500 plus 500, 1600 upward directions. Again, it remains constant now. Hence, this diagram is known as the shear force diagram. It is representing the unbalanced vertical force, that is shear force at the various sections of the beam now. Bending moment diagrams. The bending moment at a free hand for the cantilever beam is always 0 only. That means at D is equal to 0 now. The bending moment again at C is equal to the C point. It is equal to the bending moment created by 800 multiplied by the sum of force into distance, 800 into 0.8 now. It is equal to, given now, minus of 640 Newton meter now. But the effect of the beam is tends to beam in the form of convexity at the top, like this. Hence, the effect of the beam is, the effect of bending moment is treated as a negative now. Hence, it is represented as a minus 640 now, or which tends to rotate the body in clockwise directions with respect to the left hand side now. Similarly, the bending moment at B, it is equal to MB here. It is some of the moments created by the forces which are acting D and C now. That means here 800 into 0.8 plus 0.7 plus 500 into 0.7 we have to take it now. That is 800 into 1.5, that is 0.7 plus 0.8 for 1.5 plus 500 into 0.7. Both are tends to rotate the body in clockwise directions, or its effect is the convexity at the top, hence it is treated as the negative only. So it is equal to minus of 1550 Newton meter. Similarly, the bending moment at A is equal to MA. It is equal to moment created by the 800, moment created by the 500 force, and also moment created by the 300 force are all acting in the same directions now. Hence, the sum we have to take it, algebraic sum. And the effect is convexity to the top or hanging effect. Hence, the bending moment are treated as a negative now. That is it for the first one now. The distance between B and D is equal to, we are taking it here. It is equal to 2 meters now. That is 800 into 2. One is the second one is 500 into 0.7 plus 0.5. That is 1.2. The third one is 300 into 0.5. All are negative only. Hence it is equal to 800 into 2 minus of 500 into 1.2 minus of 300 into 0.5, which is equal to 600 minus 600 minus 1600 minus 600 minus 150. Total is equal to minus of 2350 Newton meter. So first select the suitable scale now. This assume again now 100 Newton meter is equal to, we are taking 1 mm length. So first of all it is a 0 at D position now. At C you have to take the distance now. At C is equal to, it is 640, it is given now. That is 6.4 mm downward directions now. Here the point load is acting. You have to join these 2 points by straight lines. Again at B, the total load is given, the moment is given 1550. So here vertically downward direction, so 15.5 mm. Again join these points again by straight lines only. At A 2350, that means equal to 23.5 mm. Again join the points straight lines. So this diagram is representing the bending moment diagram for the cantilever beam when it is subjected to 3-point loads 800, 500 and 300 to TCB respectively. Now the shear force and bending moment diagram for the cantilever when it is subjected to distributed load. Uniformly distributed load. That is the length of, it is distributed with a certain rate along the length of the beam now. Here it is the length of the beam is given now. Let AB is representing the length of the cantilever beam and carrying a uniformly distributed load W per unit length over the entire length as shown in figure. So here now, when I am taking the load at X point, it is equal to, that is a unbalanced force which is acting on the beam with respect to X is equal to, it is equal to W into X now. Where small w is representing the rate of, that is the W per unit length, the rate of loading that is acting now. X is representing the length of the beam. Hence, the total load that is acting between B and X is equal to W into X now. That is when X is equal to 0, that means here that is the point is known as the B point now. Hence, at B, the shear force is acting is equal to 0. At X is equal to, the shear force is acting is equal to W into X. It is changing according to the inclined straight lines now, like this. Similarly, when the length of the beam increases to L now, the shear force at A is given by W into L now. That is X is equal to L now. Hence, here WL you have to write vertically down upward direction and draw the lines now. So this is known as the shear force diagram for the beam when it is carrying uniformly distributed load. Similarly, bending moment at B is equal to A 0. The bending moment at X is equal to, it is the product of load multiplied by the distance between the point of application of the load from the reference. Hence, the total load is equal to W into X. The point of application means it is always at its center, that is center of gravity now. That is X by 2 now. So, the bending moment at X is equal to W into X multiplied by the X by 2 now. But the effect is, it is having convexity at the top or eigen effect. Hence, the bending moment is treated as a negative now. That means at a distance of X, the bending moment is equal to minus of total force W into X, but acting X by 2, or in other words, minus of W X square by 2 now. It is eigen effect, hence it is equal to 0. When X is equal to L now, that means the bending moment at A is given by minus half W L square by 2 now. Since it depends upon the square of the distance, the curve is, that is bending moment curve is in the form of parabolic. Hence, here now at A, Wx square, you have to join with the parabolic curve from B to C position. At the same time, at A is equal to WL square by 2, you should join the points in the form of parabolic curve as shown in figure. So, this is known as a bending moment diagram. Since the effect of this force is having eigen effect, hence the bending moment is represented as a negative. Just based on this one, we are taking one problem. A cantilever beam of length 2 meters carries uniformly distributed load of 1.5 kilonewton meter, run over a whole length and point load of 20 kilonewtons at a distance of 0.5 meters from the free hand as shown in figure. Draw the shear force and bending moment diagrams. Here the given that in the problem is the length of the beam. The length of the beam is equal to 2 meters. That is between A and B is given 2 meters. The point load is acting at B. Here 2 kilonewtons as shown in figure, and uniformly distributed W entire its length now. Now, the uniformly distributed is acting at the rate of 1.5 kilonewton per meter now. First, we have to draw the shear force diagram now. First, draw the beam according to the suitable scale and represent the forces which are acting on it as shown in here now. Now, in order to draw the shear force diagram, first of all, draw the vertical lines of 4 directions which are passing through the important points, key points as shown in figure like this, the vertical line, and draw the one horizontal lines to represent the length of the beam along the x-axis. This is known as at B. Since there is no point load is active now, only uniformly distributed load. Generally, it is represented W into X when you are taking X distance. When X is equal to 0, the force is also 0. Or in other words, when uniformly distributed load acting along the length of the beam, at a free end, its effect is equal to 0 or its value is equal to 0 now. That means the shear force at B is equal to 0 now. From B to C now, there is no force is acting between B and C. Hence, the unbalanced force between B and C is equal to W into X FC, which is equal to W is equal to 1.5 kilonewton per hour into the distance is given 0.5. It is equal to 0.275 kilonewton meter. But it is acting downward direction, so hence this value is the titular positive. Only it depends upon length, hence follow the straight line law. So you have to draw the according to the scale just 0.75 upward directions and represent. Here we are taking 1 kilonewton meter is equal to 10 centimeters and so 7.5 mm. Just you have to take it and draw the vertical lines. Join D and C, B. This is known as the shear force diagram. But at D, again at C, suddenly again 2 kilonewtons force is also acting now. And so draw the vertically additionally 2 kilonewtons, that is 2 centimeters upward, to represent the total shear force that is acting at C now. Now at E now, A point, the shear force is equal to unbalanced force. Here is equal to F, A is equal to, we can take it as W into X, that is W is equal to, W is the uniformly distributed load into X is equal to length of the beam, plus it is also acting downward directions and 2 kilonewtons we have to take it now. W into X is equal to W into L, that is equal to, W is equal to 1.5, total length is equal to 2 plus 2, it is equal to 3 plus 2, which is equal to 5 kilonewtons, that is acting downward directions. It value is positive, and so draw vertically 5 and join this point straight lines. This diagram is representing the shear force diagram for the cantilever beam when it is subjected to the combination of forces, point load as well as the uniformly distributed load. Bending moment diagrams. Again, draw the lines. This is nothing but representing the beam. Draw vertical lines from C, B, and A point as shown in figure. As per our earlier discussion, the bending moment at B is always 0 at the free hand. The bending moment at C is equal to, that is a force is equal to W into X, but it is acting at X by 2, hence this is treated as a bending moment at a point C now, that is at a distance X from the B now, but its effect is lagging effect, hence it is treated as a negative values now. When X is equal to 0.5 now and W is equal to 1.5, hence the bending moment at C is equal to, is taken as now 0.75 into 0.5 whole square, which is equal to, and the point load is also acting now in downward directions. Here now, that means it is equal to sum of 0.75 into 0.5 whole square and 2 into 0.5 is given now. So total it now becomes 0.1875 kilonewtons meter now. When X is equal to 2 now, the end position now, the bending moment is equal to here now, it is acting, it is equal to, that is M into A is equal to, entire its length uniformly distributed load is there. Total load is equal to 2 meters at the rate of 1.5 is acting, the total load. Multiply by the, where it is acting? It is acting in the middle of the beam, that is 2 by 2. Its effect is arcing effect, hence it is negative. These 2 kilonewtons are also acting now, vertically downward directions at C position now, that is 1.5 meters from A point. That is the bending moment created by the point load is equal to 2 into 1.5. It is also having effect, now, hence minus. So this entire value is equal to 6.0 kilonewton meter now. So for drawing bending moment diagrams, since the bending moment at C is equal to, here we are having, that is at a distance of X is equal to W into X by 2, it is there. That means it is nothing but proportional to the square of the distance. Hence, it followed only parabolic curve. Hence, represent the values of at c is equal to 0.1875 what we have calculated. Draw this parabolic curve between B and C. After that, A is equal to is given 6. Just join C and A again by using parabolic curve. This is representing the various distribution of bending moment across the length of the beam. So one more problem. A cantilever beam of 1.5 meters span is loaded as shown in figure. Draw the shear force and bending moment diagrams. The given that in the problem is the length of the beam is equal to 1.5 meters. That is between A and B. The point load at B is equal to 2 kilonewtons. Hence position. Uniformly distributed load is given 1 kilonewton per meter, but it is acting between C and A as shown in figure. So the length of the beam between the AC is equal to is given 1 meter because total is given 1.5, but end is given 0.5. So the remaining length this is equal to 1 meter. Now shear force diagram. Now the shear force at B is equal to here given W is equal to 2 kilonewtons. The acting downward direction so positive. At C also the unbalanced force remains constant. We can take it as 2 kilonewtons now. At A, the total unbalanced force is equal to at F A is equal to 2 kilonewtons at B. The total force is equal to it is acting at the rate of 1 kilonewton into length is given 1. So this is equal to 3 kilonewtons. This force is acting in downward directions. That means at A is equal to 3 kilonewtons. So it can be written as now drawn. First of all, draw the horizontal lines to represent the length of the beam. At B is equal to 2 kilonewtons. It remains constant up to C now. At B nothing but 3 is done by using inclined straight lines. So this diagram is known as the shear force diagram. Bending moment diagram. The bending moment at B is equal to MB, it is equal to 0 because it is a free end. The bending moment at C is equal to, at this point, it is the product of force and distance, that is equal to 2 kilonewtons multiplied by 0.5, it is equal to 1 kilonewton meter, but it is acting effect is arcing effect, it is treated as negative values now. Similarly, the bending moment at A is equal to it is sum of the bending moment created by the point load, the 2 kilonewtons. That is the 2 kilonewton into distance is equal to 1.5. It is a negative because of lagging effect. Again, the effect of uniformly distributed load we have to take. The total uniformly distributed load is equal to 1 kilonewtons into distance is 1 now, but it is acting at in the middle 0.5 now. So it is equal to minus 3 minus 0.5. It is equal to 3.5 kilonewton meter. So for drawing shear force bending moment diagrams, again draw the vertical lines in downward direction from the various points. Here it is representing the length of the beam. Since the shear force is a negative now, and moreover at a free end the bending moment is 0, at B is equal to 0, already taken now. Particularly downward direction, so you have to represent according to the scale now. 1 kilonewtons, assume 1 kilonewton meter is equal to 10 mm now. Draw 10 mm vertical downward directions. Since the point load is there now, it is now changes according to the inclined straight lines. There at A position, the value is 3.5 kilonewton meter. Here represent here now. Since it is having the effect of uniformly distributed load, it follows the parabolic curve. Hence, join these points, 2 points, by using the smooth curve isometric figure. This diagram is representing the bend moment diagrams, which is the combination of point load as well as the uniformly distributed load acting on a cantilever beam. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.